Good morning. So today we're going to be doing the last assignment in Unit 6, which is normal approximation to the binomial distribution. And so this is going to be a combination of several things that we've done in the past. Remember the binomial distribution. We're going to review that here in a second, and we're going to apply that to a normal curve. So let's go ahead and get started. So remember the problem that we did probably a couple units ago, where a person who is 20 years old has the probability of an 80% chance to be alive at the age of 65. And we did a problem like this. For number one, find the probability that at most 3 out of 5 people who are currently 20 years old will be alive at the age of 65. And so at least 3 people, could be 0 people, it could be 1 person, it could be 2 people, or it could be 3 people. And so what I'm going to do first is I'm going to take a look at this first problem here. And if you remember how we did this was we used this formula. We started with, we have 5 people and we're picking 0. So we're going to take that and we're going to multiply that times the successes, which is the success rate, which is 80%, but there's 0 of those. And then the failure rate would be 20%, and there's going to be 5 of those. And so we would multiply those numbers together to figure out just the probability that 0 of those 5 people would be alive at 80. And that comes out to be 0.0003. If we use the same formula for 1 person, remember it would look different because instead of 5 and picking 0, we would have 5 picking 1, and then we'd multiply that times 0.8 to the first power because there's 1 successful person, 1 person that's living, and then we'd take 0.2 to the 4th power because 4 people will not have been successful, and that would be 0.0064. We would do the same thing for 2 people and the same thing for 3 people, and then we'd add up those numbers together and we would get a total of 26.27% of the time. We would have at most 3 out of 5 people would be alive at the age of 65. Well, that's all fine and good. But what happens if you have a bigger problem like this? Suppose you are the manager. This is what a lot of actuaries do. Suppose you are the manager of a certain company's pension plan, and you want to know, you have all these 20-year-olds that are starting the business, and you want to know how much to collect from them so that you can pay their pensions when they retire at the age of 65. So let's say there are 500 people at this company, and you want to know what's the probability that at most 390 out of those 500 people who are currently 20 years old will be alive at the age of 65. So it's just like problem number 1, but man, is there going to be a lot more. Instead of just 4 just different numbers we're going to have to come up with, we're going to have to come up with 391 different numbers, because we're going to have to figure out the probability that nobody's going to be alive at the age of 65, that at least that 1 person is going to be alive, and then 2, and then 3, and then 4, and all the way up to 390 out of those 500 people are going to be alive at the age of 65. So that causes a problem. We probably don't want to go through what we did here 4 times. We probably don't want to go through that 390 times here. So there has to be a different way, and that's what we're going to be talking about today. And that different way is to normalize it, which means we're going to try to fit it on a normal curve, okay? And we're going to find first the average. And if you remember, to find the average in a situation like this, we're just going to take the number of people, which in our case was 500, times the success rate, which is 0.8. So the average would be 400 people. And then we also want to find the standard deviation. And here's the formula that we used for standard deviation. We have the number of people, which is 500, times the success rate, which is 0.8, times the failure rate, which is 0.2, and then we take the square root of that. So our standard deviation is 8.94. So one standard deviation above the mean would be 408.94. And then we'd have two standard deviations above the mean and three, and then one below and two below and three below. Well, so we just normalized the curve because we can say that this has the 400 has a z-score of 0. The 408.94 has a z-score of 1 and a z-score of 2 and a z-score of 3. We can even have z-scores of -1, -2, and -3 to the left. But what we want to do is we want to figure out what is the z-scores that we're talking about. And so it says find the area under the normal curve to the left of 390.5. Well, why are we using 390.5 if in the problem it says at most 390? And that's because right between 390 and 391 is 390.5. And so all those numbers that would be like 390.1, 390.2 would round down to 390. So we're going to use 390.5 and we're going to find that z-score. Remember, to find the z-score, we're going to take 390.5 and we're going to subtract the average, which we just calculated was 400, and we're going to divide that by the standard deviation, which is 8.94. That gives us a z-score of -1.06. Well, then we're going to use our calculators to find the z-score of the area under or to the left of -1.06. So let me change. -1.06 is about right here. We want to find this area right here. So we're going to go to our calculator, and if we have a graphing calculator, we're going to go to second vars and go down to normal CDF, and we can type in -10 for our lower limit, and our upper limit is going to be -1.06. And then we can go find that area, which is 0.1446 if we round it, 1.4457. So that's 1.446, which is about 14.46% chance that we would have at most 390 people would still be alive at the age of 65. And then knowing that number, we would know how much to charge those people so that we could have enough money in the pension plan so that everybody would get paid when it's time for them to all retire. So real quickly, this is what we did here. We normalized the curve. And so let me advance to the next slide here. Okay, so here we go. So we did that normal, we did that by converting it to a normal, that binomial distribution to a normally distributed curve. Here's the problem though. Not all of those binomial distributions are normally distributed. So as n gets bigger, it gets closer and closer to being normally distributed. Let me show you what I mean by using this slide. So here we have only 5 people, and the probability of a success is 0.3. This is one of the slides that we used earlier on, but you can see this graph is not normally distributed. Now, as the number of people gets bigger, like here we have 10 people, the probability of success is still 0.3. It looks a little bit more normal. And then if we have 20 people, it's even more normal. So we can say it's pretty close to normal if we have a bigger sample size, a bigger number of people. Now, we don't really have to worry about this if the success rate is 0.5, because in this, the orange graphs, they're all normal. And that's because the success, you have a 50% chance of living and a 50% chance of dying, so it's going to be symmetrical. But here, if the success rate is 0.8 and we only have 5 people, well, then it's not very normal. This is skewed to the left. It's a little bit more normal if we have 10 people, and it's a lot more normal if we have 20 people. So we can't always count on the fact that we can take a binomial distribution and normalize it. And so there's going to be a plan, a strategy for us to figure out if this will work. And so here are the steps that we're going to take in order to do what we just did. We're going to have to find n, which is the number of people. the number of trials, and the success rate. And we could normalize it. We can assume that it's going to be normal enough to estimate it with a normal distribution if two things happen, okay? And that is, like in the last example that we had the number of people was 500 and the success rate was 0.8. So if we multiply those together, this example, that's 400, okay? That's this one. And then we're going to take the number of people, which is 500, times the failure rate, 1 minus p, which in this case is 0.2, that's going to be 100. You can see our numbers are 400 and 100. They're both greater than 5. If those are both greater than 5, then we can say it's going to be normal enough to use that normal distribution to find the z-scores, find the area under the curve so that we don't have to go through 391 different steps. Now, the first example that we did in class was where we only had 5 people, and the success rate was 0.8. Well, if I take 5 times 0.8, I only get 4. If I take 5 times 0.2, which would be the failure rate, I only get 1. So we could not use this with only 5 people. It wouldn't be normal enough. But with the bigger numbers, it does become normal enough, which means we can normalize that binomial distribution. And then we could just follow the same steps that we did before. We found the average, we found the standard deviation using these formulas. Okay, those are going to be important formulas when it comes time to take your test. And then we can find the z-scores. And once we find the z-scores, we can find the appropriate area underneath the curve. Okay, so let's just take a look at this last example. Suppose you take a true or false quiz with 10 questions and you guess on all 10 questions. You want to find the probability of getting 7 or 8 questions correct. Well, so we want to first figure out if we can do this. We know that n is equal to 10, and we know that the success rate is 0.5, so that's what p is equal to. So let's just first figure out if this is possible. If I take n times p, well, that's 10 times 0.5, which is 5. And then if I take n times the failure rate, which is 1 minus p, that's also 10 times 0.5, which is 5. So because both of those are 5 or bigger, we could normalize it. And so what I'm going to do here to normalize this curve is I'm going to first figure out what the average is. The average is going to be 10, which is the number of people, times the success rate, which is 0.5, so the average is 5. Then I'm going to find the standard deviation. The standard deviation is the square root of 10 times the success rate times the failure rate. Well, I'm going to need my calculator for this one. So if I take the square root of 10 times 0.5 times 0.5, I get 1.58. Okay, that's a rounded number, but that's my average. So then I can take my scores that I'm interested. Now it says from 7 to 8, but I'm going to go from 6.5 to 8.5 because I want to include all the numbers that would round up to 7 and would round down to 8. And I'm going to normalize that, which means I want to find the z-scores. So to find the z-score for 6.5, I would take 6.5, that's my x value. I'm going to take 6.5, and I'm going to subtract the average, which is 5, and then I'm going to divide that by 1.58, which is the standard deviation. Well, that's 0.949. I'm going to make that 0.95. That's the z-score for 6.5. Well, then I'm going to find this z-score for 8.5. which means I'm going to take 8.5 and subtract 5 and then divide that by 1.58. And that gives me 2.215. So I'm going to just make that 2.21. So those are my z-scores. Then I would use my calculator to find the area between those two z-scores. And if I find the area between those two z-scores, remember I'm going to go to second vars. I'm going to go to normal CDF. My lower limit, my lower z-score is going to be 0.95. and my upper z-score is going to be 2.21, and I want to find the area underneath that curve, which is 15.7 or 0.1575, which is 15.75%. So that means I would have a 15.75% chance of getting a 7 or 8 on a 10-question true or false quiz if I was just guessing. Now, let me just finish this slide here, because hopefully you can read these in different colors. If we were to use the binomial distribution formula, and we did the binomial distribution formula for 7 and we did 8, just like we did at the beginning of this PowerPoint, we would have gotten 16.11%. Okay? But if we do, if we normalize it and find the area underneath the curve, we get 15.78. And I must have used, when I did this, I must have used a different estimate. Maybe I didn't use 2.21, but maybe 2.215. And so they got 15.78 instead of 15.75. So you can see those numbers are not exactly the same, but it's an estimate. And that gives us a really good estimate by normalizing the curve. And that's what 6.5 is about. And that's what our homework assignment is going to be about today as well. So real quick, this slide real quick shows you why we need to use the 6.5 and 8.5. We wanted to find the area of two rectangles, which is the area for 7 and the area for 8. But that means we'd have to start at 6.5 and go to 8.5 and estimate it by finding the area underneath that curve, which is this area here. And that is what we did with that assignment. So that's 6.5. Hopefully this video was helpful. If not, we will go over things in class or in our Zoom meeting, and we will see you all soon.